All right, so here we are. Now we're working. All right, so we're still doing the product rule and the quotient rule, 62.4. Here's another type of question that could show up pretty easily on multiple choice free response. You've got a table of values. We've seen that before. You have values for two values of x, and then you got their f and f prime values and their g and g prime values. So short of being given an actual expression that we can manipulate, we can actually find derivatives symbolically and then use the table or the chart to plug things in. So that's what this says. Use the table above to find the values of the following derivatives at the selected value of x. So we want to find h prime is 0 if h of x is equal to that. So this would be the noun format. So before we can find h prime is 0, we got to find h prime of what? X, right? We got to find the derivative function first. So you go over to h and you see, he's made up of two functions that are being divided. So this is going to be the quotient rule. So h prime of x is ho d high minus high d ho all over ho ho. Now, when you're taking the derivative, you could do it with just their names. It saves a little bit of writing. The of x is just the independent variable. So maybe I wouldn't even have h prime of x there. I would just have h prime. So that would earn credit for the derivative, right? If they were testing that, that would be probably right there, maybe 2 checks actually. And then when you plug in, we're going to plug in a what for x? A 0. So now we need to say, okay, h prime of 0. Now, if you want, you could go ahead, let me put this as an asterisk line. You could say that's g of 0 times f prime of 0 minus f of 0, g prime of 0, all over g of 0 squared. You could do that, or what else could you do? That's a lot of writing. You could go straight to the plug-in. If you put h prime of 0, you can actually get straight from here to here, okay? By just saying, okay, that's going to be g of 0. So what is g of 0? We come up here, and we see g of 0 is 5. F prime of 0. So this is not difficult. You just don't want to be very deliberate. F prime of 0 looks like it's negative 3, yeah? And it's even harder with an iPad because you get this tunnel vision, right? You have to zoom in and zoom out. When you actually have just a piece of paper, you just, let your eyeballs wander. F of 0 is 2. Y prime is 0. I'm sorry, G. See that? I can't even read my own writing. G prime of 0 is negative 1. And then, of course, G of 0 is 5, and we're squaring that. So if this were a free response, if you did not show this line right here that's highlighted, that would be fine. Could you stop on that bottom line? Yeah, free response, you definitely could. Multiple choice, we would keep going. So that's negative 15 plus 2 all over 25, and it simplifies to negative 13 25ths. So we don't know much about that function, but we do know that h at x equals 0 is decreasing. Right? It's going down 13 for every 25 it's going to the right. And so we could do something similar for something like this. So notice this one now, another function h, that's x times f times g. How many factors now? 3. So with the product rule, how many terms are we going to have? 3, right? So before we can find h prime of negative 1, we got to find h prime of x. So h prime of x. I'll go ahead and put of x this time. What would be the derivative then of x? We'll do it like this. First, second, third. So that becomes 1. And again, you don't have to show the 1, but I do it for accounting purposes, right? I know that I've taken the derivative of something and it happens to be 1, rather than if you just wrote f times g, it looks like maybe, that you forgot to do something. So it's entirely up to you. But f times g, and then plus x times f prime g, and then plus xf times g prime. So I can have the of x on the left or not. It doesn't really matter. But that would earn credit for the derivative. And now we'll go h prime of negative 1. So I'm going to try and do this one without writing f of negative 1, g of negative 1. Let's see if I can just go straight to the plug-in here. I'll zoom out enough. Okay. So f of negative 1 is 3. G of negative 1 is negative 2. Plus. Now in this middle term, what do I do for x? X is not in the chart. Yeah, it is given to be negative 1, yeah. So then f prime of negative 1 is 4. and g of negative 1 is negative 2. Notice I'm using parentheses instead of dots. And then negative 1, f of negative 1 is 3, and then finally g prime of negative 1 is 2. So not difficult, assuming you have the right derivative, a little bit meticulous, right? You have to be a little bit tedious to get all those values in there correctly without, making a careless mistake. So free response, you're essentially done. Multiple choice, of course, we're going. That's negative 6. That ends up being positive 8. And then minus another 6. So that's going to be negative 4. Okay? All right. Not so bad, right? Pretty good stuff. And of course, we could do the same thing with like sine and cosines and power rules if we had them. You just have to know that if you end up needing something to plug in and it's not in the chart, then something went wrong. Later on, we get to the chain rule. It gets a little bit more exciting. All right, any questions on that? Symbolic differentiation. All right, so the last one, true story. True story. All right, let's read it. The position for a falling object on or near the surface of the moon. Okay. This says approximately within 6 feet or so. Is given by this. H of t is negative 2.66 t squared plus h sub o, where h of t is the height in feet at any given time, and t is in seconds. H sub o is the initial height in feet. All right, so this is a kinematic equation for a falling object, but it's not on planet Earth. It's on planet Moon. So the Earth equation you might recognize, right, from physics. It would be negative 16 t squared plus v sub oh plus h sub o. Very similar, but the coefficient in the front is different because of the effects of gravity, right? Which are what on the moon? Greater or less greater? Lesser or more? Yeah, lesser. Yeah, on the moon. Okay. So some people think the moon is actually zero gravity, but that's not true, right? If you've seen the fake videos of the moon landing, you see that they're actually trying to portray people like having less gravity, but still gravity, right? Okay, cool. Part A. If you were eating at an Italian restaurant on the moon, great food, but no atmosphere. And your meatball, okay, so I guess you're eating, yeah, and your meatball rolled off the 3.2-foot high table, okay, so you're kind of into it, and look, notice you're inside. This is an actual photograph of the pizzeria, Italian joint. Anyone ever been there? Yeah, me neither. I just stole this image off of GooglePhotographs.com. And anyway, so you can see that they're inside, looks like something with a controlled environment, and they're eating at that 3.25 table. Maybe the meatball's on the pizza. You can kind of see how they're carelessly holding the pizza wedges there. And that's either their second pizza or one of them stole a piece from someone else because, the two pieces they have don't seem to fit back in the pie that they have. But, I wasn't there, and this is the only picture I have, so I don't know what's going on to the left or right. But let's say that one of their meatballs on their pizza has already fallen off. You see that? It's not there. And it's going onto the floor. After how many seconds, then, would it take for it to hit the floor? And then how fast was the meatball traveling when it hit the ground? All right. So we kind of did this with the falling book, but now we're on the moon, and we got meatballs, right? So what are we going to do? How are we going to figure out, it says, for how many seconds did it take to hit the floor? What do we know about? This is our only thing to work with.
0 would be our ending height.
Right, 0 would be our ending height. So I know that h of t is going to be negative 2.66 t squared plus, if it fell off a 3.2-foot high table, or we could say maybe, this is 3.2 and there's his green meatball or whatever, because he's got his as an angle. She looks like she's trying to balance a meatball, So maybe it was him. That makes sense, right? The girl's got it all down. Boys kind of just, reckless and, yeah. 3.2 feet. So then we set it equal to 0. So we created the equation, and then we showed what we're solving. All right, so let's solve that. So that's going to be positive 2.66t squared equals 3.2. And to solve for t squared then, we'll divide 3.2, 2.66, and we take the square root of that. Remember, we always consider plus or minus. Do we want the negative value of time here? No. Do we always just dismiss negative values of t out of hand? No. Because sometimes they're good for extrapolating backwards to a point in time that did exist before we got there to set up the model to describe the behavior. But in this case, that would be going back in time before the meatball even left the table to hit the floor, so it wouldn't make sense. So there it is. That's a number we can all appreciate, right? Yeah. Mr. Bird, did you happen to get that number? Oh, okay. Yeah, this is somewhat of an exact number, right? I don't want to take the time to load mine, but 1.096. Good, 1.096 seconds. Thank you. Thank you very much. So that is that reasonable? It took just a smidgen more than a second for a meatball to fall off a 3-foot table and onto the floor. Okay. Would it take on Earth? Would it fall faster than that, or take less time, or more time? Same. All things considered the same. Same table height, same meatball consistency. It would take less time, right? So yeah, 1 second seems like a long time to fall, right? But that's on the moon. Okay. So now part B. How fast was it traveling when the meatball hit the ground? Is that instantaneous or average velocity? Instantaneous, when it hit the ground. So we're going to need the instantaneous velocity equation for a falling object on or near the surface of the moon, and that is known as the big D, not Dallas, not after yesterday. The derivative, right? So negative 2.66 times 2, that's going to be, negative 5.32. T to the first, right, power rule, and then plus 0. So there it is. And now, what are we going to plug in for t? The time. Yeah, now here's kind of a little tip, right? We don't want to ever use a rounded or a truncated number for a subsequent calculation. All right? Let's see if I heard that. When do we want to use a rounded or a truncated non-exact number for a subsequent calculation? Never. Ever, okay? So there's a couple ways to do it. If this number is still in your calculator from the previous line, you can write h prime of 1.096, okay? Sometimes I put ... after that just to remind us that we want to use the answer in its full decimal glory. You could just then, on your calculator, type in negative 5.32, and then you can hit second negative, right, which brings up the answer from the previous line. And it looks like that. Or you could also do this. That we'll be doing this a lot. If that number is on your calculator, you can hit stow alpha A. And if you store it as like something besides X on your calculator, stow alpha A, enter, then you call it A on your paper. And the benefit to that is if you are going to be plugging it in, you could just write it like that for an intermediate, okay? Or you could put H prime of A, and it reminds you where you stored it. So then you type that in, and what do we get there? Did y'all do that one?
Negative 5.835.
Okay, 835. Good. And that would be units of what? If it's the rate of change of position, it would be velocity units feet per second. Okay? Let's go ahead and write a sentence. It doesn't say to do that, but this is one of the things we're going to be doing a lot of. The question could then say, explain what this number means in the context of the meatball's position. Okay? So you would say then, at t equals 1.096 seconds. So just like when you're evaluating a function, you always start with the independent variable. When you're writing a sentence, you always start with the independent variable, which is, for an average rate of change, it's an interval of time. For an instantaneous rate of change, of course, it's a moment in time. And this is the easiest way to get credit. T equals, and you have your unit there, comma, you could say the meatball's height is decreasing, right? That would work. But we could refine that a little bit better without the risk of messing up. What else could we say besides the meatball's height is decreasing? Well, we want to describe it in terms of the height of the meatball. Instead of just saying its velocity or its speed is 5.835, we could say the meatball is whatting? Falling, right. So that's good. It's falling. That implies downward, right, at positive 5.835 feet per second. So that would be kind of interpreting it as a speed with the direction. Okay? Or you could say the meatball is, let's put this, the meatball is ... So there would be an asterisk. That would be interpreting velocity as a speed with the direction. But you can also interpret it in terms of its height. So the meatball's height is decreasing by 5.835 feet, and you actually write that out, each or per second. So how do you know which one to write? Well, the question will tell you, what does this mean in terms of the meatball's height? What does this mean in terms of the meatball's velocity? So if it says, what does it mean in terms of its speed or velocity, you would give an answer of speed in a direction. If it says in terms of the height, you would just say if the height is increasing or decreasing. And notice really the only difference is how you answer with the units. If it says in terms of speed or velocity, you use velocity units. If it says in terms of the meatball's position, you would use position units in your sentence and then per whatever. But you always interpret a vector in a sentence by interpreting the magnitude and then the direction separately, okay? So you always talk about the scalar magnitude and then increasing or decreasing by that amount. All right, so anyway, it hits the ground at 5.835 feet per second. So now the next question is, if you retrieved it within 5 seconds, would you still eat it? I would, right? There's not a lot of food on the moon. You got to eat what you can, right? Does the 5-second rule still apply on the moon? Yeah, I think so. Right. Now, it depends. I mean, 5.83 feet per second, depending on the meatball, it could hit and kind of like disintegrate, possibly. You go, then you got like little meatballs everywhere. I don't know. Using the given equation above, determine how many times stronger the acceleration due to gravity is on Earth than the moon. How are we going to figure that out? H double prime. Good. The second derivative of position ends up being the first derivative of velocity. Now notice I never called H prime velocity. So if I'm using V down there, I might want to come up here and call that V of t. And then down here call that V of 1.096. So this right here would define the velocity function for you. Okay? Now you wouldn't have to say H double prime at all down here if you didn't want to. Since I defined V above, you could just say V prime of t, and then I'll go ahead and call it A of t. And it would equal, if you take the derivative, you get negative 5.32. So that would be on the moon. And what's the acceleration due to gravity on Earth? Negative 9.85 meters per second, but we're measuring this in feet per second squared. Yeah, it'd be negative 32 approximately feet per second squared. So I'm calling that E of t, the acceleration of gravity on Earth versus the acceleration due to gravity on the moon. So we tend to use feet a lot in here instead of meters. So if we want to figure out how many times stronger, all we have to do with those is what? Divide them. So the scale factor is going to equal, let's do the big divided by small, 32 divided by 5.32. Anyone got that? 6.015. Okay, so that might be a number you want to store as B if you get that. So approximately 6 times. Okay, it's approximately 6. And so now, based on that, how much do you weigh on the moon? Determine your own weight. Okay, I'll go ahead and do mine. You go ahead and do yours. How much do you weigh on the moon? I'm doing my math wrong. 13 pounds. Sweet. I would only weigh 40 pounds on the moon approximately. Does that solve your diet problem? You're lighter, right? So there's less strain on you when you're walking, right? But your pants still don't fit. Yeah, it only makes you lighter. It doesn't make you physically smaller. So Thank goodness for elastic waistbands. All right. Have fun eating at lunch. Protect those meatballs.